Уважаемые коллеги, меня слышно?
Да, Александр, мы вас слышим.
Добрый день, коллеги.
Вы загрузите? Да,
Да, давайте, попробую.
давайте.
Ага,
Sharing.
сейчас. Так. Ну, что-то видно сейчас или нет?
Пока нет.
Пока нет.
Нужно
Так,
share screen сделать.
сейчас, я понял, да, сейчас. И сейчас тоже не видно, да? Да, сейчас, одну секундочку. Так, демонстрация экрана. Ну, вот это вот.
Так,
А
начинает
сейчас?
появляться. Появилось.
Появилось, да?
Появилось, да, но пока да, все слайды.
Вот так вот, нормально?
Да, вот все отлично.
Ну, университет виден, хорошо.
Да, университет
А,
отлично.
ага, и листается, да?
Да, и листается.
И звук есть, я так понимаю, да? Ну, все, шикарно.
Слышим.
Ага.
Сейчас еще минутку и начнем.
Ну, давайте, да, хорошо, спасибо. У нас язык английский, да? Я понимаю.
Еще раз?
У нас язык
Да,
английский.
английский.
Ну, да. Я так, естественно, да. У меня слайды на английском.
Отлично. Okay, let us start our morning session. The first speaker today, Alexander Studenikin, with the talk Electromagnetic Properties of Neutrino.
Well, good
40
morning.
minutes.
Yeah, thank you very much. Good morning, everybody. It is really a great pleasure and honor for me to have this chance to present, I would say, a wide review on neutrino electromagnetic properties on this well-known and very prestigious workshop on high energy physics. And I am very thankful to the event organizers, in particular Vladimir Petrov, for inviting me. And I regret I am not able to participate in person. So the plan is as follows. First, I remind the basic things related to neutrino electromagnetic properties. Then we deal with constraints on the most important neutrino electromagnetic characteristics, such as neutrino magnetic and dipole moments, midi charge of neutrino, and even the charge radius of neutrino from laboratory experiments. Then we turn to astrophysics and also examine a manifestation of neutrino electromagnetic interactions in different astrophysical environment, and also consider astrophysics as a probe, efficient probe on neutrino electromagnetic properties. And at the very end, I will discuss some new effects in neutrino oscillations related to neutrino electromagnetic properties, and then make an announcement and advertise some new projects on the study of neutrino electromagnetic properties that we are now running. So the most wide and complete review on the subject can be found in our paper published several years ago together with Carlo Giunti in the Reviews of Modern Physics, entitled Neutrino Electromagnetic Interactions and Window to New Physics. Indeed, this problem, neutrino electromagnetic properties and possibility to measure neutrino magnetic moment, arise even before the experimental discovery of neutrino in 1956. Up to now, nothing has been seen All results of terrestrial laboratory experiments, I should say the truth in the very beginning, on neutrino magnetic moment and also other electromagnetic properties, as well as data from cosmology and astrophysics, are in agreement with zero neutrino electromagnetic properties. However, due to the most recent discoveries in neutrino physics, we know that neutrino mass is not zero, and therefore we can say that neutrino electromagnetic properties open a window to new physics, because in the stellar model with the massless neutrino, there is no room for no neutrino electromagnetic properties, and the magnetic moment in particular is zero. However, even in the easiest generalizations of the stellar model, when the mass is not zero, in one loop calculation for Dirac neutrino, it is possible to show that magnetic moment is not zero, and it is proportional to the mass of the mass states of neutrino. If we put the present cut-in limit on the effective mass of neutrino, we get that magnetic moment in this version of generalization of the standard model is 3 × 10⁻⁹ per magneton. Well, it is really many orders of magnitude smaller than the present experimental limits, which we shall discuss in some detail. From reacting neutrino, that set a limit on the level of 10⁻⁻11 per magnetons from GEM experiment. From astrophysical considerations, the limit is slightly better, up to 10⁻12 per magnetons. So also there are limits on neutrino Milli charge, and the most severe bound comes from neutrality of the hydrogen atom, that is 3 × 10⁻21. However, there are other investigations of manifestation of neutrino Milli charge in astrophysics, and I will just also flash on the most severe bounds, astrophysical bounds on neutrino Milli charge from astrophysics. So a few words about the theory. So electromagnetic interactions of neutrinos are described by the so-called electromagnetic vertex function. And from Lorentz covariance and electromagnetic gauge invariance, it is possible to get that the vertex function can be decomposed in terms of 4 form factors, which that are the electric, dipole magnetic and electric, and the anapole form factors. So this is the most general decomposition. And if we imply the hermeticity and the behavior of electromagnetic current under discrete symmetry transformation, we can put further constraints on the form factors. And just here we have to distinguish the Dirac and Majorana neutrinos that exhibit quite different electromagnetic properties. Well, for instance, for a Majorana neutrino, 3 from 4 form factors should be 0. It was pointed out even Pauli many years ago. So here we can conclude that in principle, the study of neutrino electromagnetic properties can be used as a tool to distinguish the nature of neutrinos, whether it's a Dirac or Majorana particle. So in some more general theoretical framework, it is possible to consider the transition between different mass states, and in such a way, form factors are matrices in neutrino mass eigenstate space. And again, the Dirac and Majorana neutrinos exhibit quite different electromagnetic properties, and Majorana neutrinos can have of diagonal magnetic moment, for instance. So yeah, I have mentioned there is diagonal and transition of diagonal magnetic moments. And again, I would like to flash once again that electromagnetic properties can be used to solve the question whether neutrino is Dirac or Majorana particle. Some more detailed consideration of neutrino vertex function that was done in our paper about 20 years ago with Dvornikov. We calculate the vertex function accounting for form factors in the most general theoretical approach using the renormalized gauge theory. And we examine in one loop level the contribution of different diagrams to different form factors, and that accounting exactly for the masses of all particles, including the exactly accounting for the mass of a neutrino. And this study enabled us to consider the dependence of the neutrino magnetic moment on the neutrino mass. And there are two parameters that are important here. That's the ratio of neutrino mass to W mass and the lepton mass, charged lepton mass to W. And we have shown that the physical value, the magnetic moment that is form factor at Q squared 0, indeed is not dependent on the gauge fixing parameter. This is really a physical value. And also we derived for different scales of the masses of neutrinos, for the light neutrino, for the intermediate value mass of neutrino, and the hypothetical heavy neutrino, we derived the explicit expressions for contributions to the magnetic moment. And always within this class of theories, we show that the magnetic moment is proportional to the neutrino mass. So it is also possible to include the effect of mixing in this game and derive the one loop contributions to the magnetic and electric dipole moments, accounting for mixing. And from this explicit expression, this follows that transition moments vanish because of the unitary of the mixing matrix. And again, there is a difference between the Dirac and Marana case, and in Marana case only of diagonal magnetic and electric dipole moments exist. So this suppression, Jim suppression of the magnetic and electric dipole moments result that these values are even much smaller than the value for the diagonal magnetic moment. And also we can conclude here and expect that neutrino radiative decay is that could proceed due to non-trivial neutrino magnetic effective magnetic moment is a very slow process. So indeed, there is a big problem to have a visible value for neutrino magnetic moment, as well as from theoretical point of view, and also for the experimentalist. So if we consider some theoretical framework beyond the standard model, and if we suppose that some new physics are characterized by the scale lambda, then the additional diagram will contribute of new physics to contribute to the neutrino magnetic moment, and it is possible to calculate that this additional contribution due to new physics to magnetic moment is inverse proportional to the scale lambda. The same diagram will also shift the mass of neutrino, and again, very easy calculations shows that the additional contribution to the mass will be proportional to lambda. Combining these two estimations, we get that there is a relation between new contribution to the mass of neutrino in this theoretical framework beyond the standard model and the magnetic moment contribution. And if we expect that if we wish to have a magnetic moment contribution much bigger than the standard model prediction easiest generalization of the standard model prediction on the level 10 to minus 18 or 19, then we will get unacceptable big contribution to the mass. And this is a big problem for the theorists who are trying to consider some theoretical framework beyond the standard model, aiming to get much bigger values for neutrino magnetic moments than the prediction of the easiest generalization of the standard model. However, there are some theoretical frameworks like the left-right symmetric models that can give rather big contributions to the additional contribution to magnetic moment, which are not proportional to the effective to the mass of neutrino, but and the contrary are proportional to the mass of the charged leptons. So, and there are other possibilities, other models that also predicts much bigger values for magnetic moments of neutrinos. So, about a remark about an electric charge of neutrino. So, in the standard model, the neutrality of neutrino is attributed to the gauge invariance of the theory and also anomaly cancellation constraints. And these two prescriptions result in quantization of the charge, electric charge. And so in the standard model, there is no room for a charge of neutrino. But strict requirements for charge quantization may disappear in extensions of the standard model. And in these models, the hypercharge can be dequantized, and as a result, also the charge, electric charge, become not quantized. And in this case, there is no inherent limits for the charge, only the experimental observations and on the charges of the particles set a limit on neutrino Milli charge in this case. So, however, we know that the charge of electron is equal to the charge of a proton, and also the neutron is neutral. Hydrogen atom is also neutral to the level of 10 to minus 21. So it means that only this experimental observation set a limit, in this case, on the Milli charge of neutrino. But nevertheless, there are a lot of efforts by theorists and experimentalists to investigate the possibility of a neutrino being a Milli charge particle. So, although usually it is assumed that the neutrino is electrically neutral, however, even in this case, we can introduce the so-called charge radius of neutrino, and that also is a very important manifestation on possible manifestation on trivial neutrino electromagnetic properties. And also this Milli charge, this charge radius is closely related to the anapole moment, and in literature we can often come across a claim that in the standard model of massless neutrino, anapole moment is equal or identical to the charge radius. But in fact, this is not quite correct statement. So the fact is that in this case, the anapole and the charge radius, they contribute simultaneously together. There is a mixture, and it's not possible to distinguish whether it is an anapole or this Milli charge. So this is a more correct statement about relation of the Milli charge and the charge radius. So about the experimental constraints on neutrino magnetic moments, Milli charge and charge radius. So there are a lot of experimental investigations and a lot of constraints, and they are usually just listed in the reviews of particle physics by the particle data group. So indeed, the magnetic moment is the most easily accepted and the most natural, I should say, among the electromagnetic properties of neutrinos. And in the terrestrial experiments, the most severe bounds on neutrino magnetic moment arise from the studies of neutrino electron scattering. The cross section on scattering of electrons. The cross section is composed of two terms: the standard model contribution and the electromagnetic contribution that is proportional to the square on the effective magnetic moment of neutrino. So here is the plot of the two terms, the standard model and the magnetic modeling contribution to the scattering on neutrino on electrons. This is dotted black line in L flat stands for the weak contribution, and the colored lines show the contribution of electromagnetic properties due to non-trivial neutrino magnetic moment for the values of effective magnetic moment of the 3, 4, or 5, 10 to minus 11 Bohr magnetrons. So it is easy to see that the lower the electron recall energy measured is, the most easier to see the excess of in the cross section due to magnetic moment contribution. So the best limit, terrestrial experiment limit, with the use of direct antineutrinos have been obtained by the JEMA collaboration on Kalinin atomic power plant in Udomla. This is a joint venture of Joint Institute for Nuclear Research, Dubna, and ITEP, Kurchatov Center. And from 2012, the best limit that was obtained by this experiment is on the magnetic moment is 2.9 10 to minus 11 Bohr magnetrons. Now, a next edition of the JEMA experiment, new GEM experiments searching for coherent neutrino electron nuclear scattering, is now running, and quite recent new results have been published, and we hope that probably soon a new evaluation of the possible contribution of non-trivial neutrino magnetic moment will be announced, and according to the very low threshold that have been achieved in this experiment on the level of 200 eV, the sensitivity to the magnetic moment will be lower to something 5 from 9 10 to minus 12 Bohr magnetrons. We are waiting for new results from the new GEM experiment on neutrino magnetic moment. So this is some description. So probably I will skip this part. So together with my colleague Konstantin Kuzakov, we about 10 years ago we managed to criticize and to show that the attempt of our colleague from Taiwan, from Texon experiment, to be more sensitive to the magnetic moment of neutrino was ruled out. So colleagues erroneously calculated the effect of atomic ionization. So they just include that the fact really that the scattering, neutrino scattering, is not on free electrons but on electrons that are bound, and incorrectly re-estimated the electromagnetic contribution. But in the series of our papers, we show that they are not correct, and that the free electron approximation is quite appropriate for analysis of this experiment for these energies. So another important constraint on neutrino magnetic moment come from the solar neutrino fluxes, and Boroxina announced in Kyoto conference announced the upper bound for effective neutrino magnetic moment on the level 2.8 10 to minus 11 Bohr magnetons. Well, what is important to note, so the observable magnetic moment indeed is an effective parameter that depends on the type of experiment and depends on neutrino flavor composition at the detector. Therefore, the implications of different limits from different experiments are experimental dependent. So in different types of experiments with different fluxes, different sources, different distances that neutrino travels from the source to the detector, different effective magnetic moments are checked. So, and this fact was examined and studied in detail in our paper on neutrino electromagnetic properties in low energy elastic neutrino electron scattering. And we perform a comprehensive analysis of neutrino scattering with the count for effect of mixing and oscillations. So I skip these details, and we show that depending on whether this is a short baseline experiment or a long baseline experiment, different effective magnetic moments are checked. So this is the set of most important limits on the neutrino magnetic moments from the particle data group and from our paper, review paper. So I would like to add here that about 10 years ago, just examining the available data from JAMA neutrino electron scattering experiment, I just added to the cross-section an additional term that might arise if neutrino is a mealy charged particle. So this is indeed the third unobservable in the experimental term, and from this fact, it is possible to constrain the mealy charge of neutrino. And the limit was obtained on the level something 1 10 to minus 12 charge of electron. And since 2016, this bound is in the table of particle properties, neutrino properties that are published by the particle data group. So with the expected new sensitivity of a new edition of the JAMA experiment, new GEN experiment, the sensitivity to the mealy charge of neutrino can reach the value of 10 to minus 13 charge of electron. So about charge radius. So one of the important results of our paper, I have already mentioned above, is that the effect of neutrino flavor transition mealy charges and charge radiuses are important. And in particular, we just stated that contrary to the usually accepted statement that the charge radius in neutrino electron scattering can be considered just only as a shift of the vector coupling, and we have shown that this is not correct, because not diagonal in flavor basis charge radius can also appear. So, and using this observation together with our Italian and Chinese colleagues, some years ago, we examined the coherent experiment data and put for the first time bounds on electromagnetic neutrino charge radius, including the first bounds on the transition charge radius. And these values also are included now in the table of particle properties by the particle data group. And moreover, the editors of PRD choose this result among the most important results published in this journal in 2018. So I just keep this. This is electromagnetic properties in astrophysics. So I suppose I have about 12 or 13 minutes. Am I correct?
Yeah, that's correct.
Yeah, thank you very much. So now let's turn to astrophysics, and also let's discuss briefly the bounds and manifestation of neutrino electromagnetic properties in astrophysics. So this is a set of the most important neutrino electromagnetic interactions that can arise due to non-trivial neutrino electromagnetic properties. This is the neutrino decay. Also, the same diagram describes the Cherenkov radiation of neutrino, and also a new process that we have proposed about 20 years ago, really, a spin light of neutrino in matter. So there is a plasmon decay into neutrino and antineutrino, and this is one of the most important from the astrophysical applications processes, because even this particular process set the best upper bound of effective neutrino magnetic moment from astrophysics. There is also scattering of neutrino or lectrons or nuclei, and also there is a spin precession and oscillations of neutrinos in external electromagnetic fields, and also moving matter. So I will just skip this neutrino radiative decay because really it can be used to set limits on effective neutrino transition magnetic and electric moments, and also I will just skip this. This is the process of the neutrino Cherenkov radiation. Also, the summary here is, if you just consider the magnetic moment from 10 to minus 11, then in the solar fluxes we shall have about few photons per day. So in the big volume detectors. So there is different other possibilities for neutrino Cherenkov radiation, also that might be interesting from the point of astrophysical applications. So a few words about the new effect that we predicted several years ago with our colleagues, and we call it the spin light of neutrino. The point is that neutrino with non-zero electromagnetic properties, in particular magnetic moment, while moving in dense environment, can emit light, very similar to the electron that emits light moving in the magnetic field. So, and we just quite recently, about 5 years ago, we just examined the spin light of neutrino in different astrophysical environments. This effect is due to the spin precession of neutrino in the environment. And first, we developed the quasi-classical theory for neutrino spin evolution in external matter. So, in addition to the magnetic field term, we just put here and calculate additional term that is due to weak interaction of neutrinos with matter. We just invent this spin light of neutrino due to an analogy with the classical electrodynamics, where the charge zero object with non-zero magnetic moment can emit light that is proportional to the second derivative squared of magnetic dipole moment of a system. So, indeed, the spin light of neutrino is. Hello? Do you hear me?
Нет, посидел тут на компьютере.
So okay, thank you. So indeed, the spin light of neutrino is a quantum phenomenon, and we developed the quantum theory of this phenomenon. We consider initial neutrino state in matter that is described by the wave function of neutrino accounting the density of matter. The photon is coupled to neutrino by the non-trivial magnetic moment. And we develop an approach that is very well known in quantum electrodynamics, the so-called Fourier representation. When you, for instance, consider the cyclotron radiation and you just use the wave function for electron as the exact solution for the Dirac equation of electron in the presence of magnetic field. We did the same, but for neutrinos, but instead of magnetic field, we just used the background method. So we developed this method. We just take this method from electrodynamics and apply it to neutrino in dense environment, in dense matter. So, this is the diagram for neutrino spin light. These initial and final neutrino states are described by the exact wave function of neutrino, accounting for the dense matter. F is the matter current and matter polarization depending on the density of matter, and we consider the spin light as a transition of the excited to low-lying neutrino state with emission of a photon. So we examine the different properties, the angular distribution, and make some estimation. Of course, the effect is very, very small because it is proportional to the effective magnetic moment of neutrino. And also we account for the plasma effects, and again examine in this paper different possibilities for astrophysical application of this effect, and have found that there are some extreme astrophysical environments provided by the gamma ray bursts where this light might be thought to be visible. Okay. This is our very recent paper where we also consider the spin light of neutrino in moving matter, and also discuss some astrophysical applications. So now astrophysical bounds for magnetic moment, effective magnetic moment, I have already announced that the most severe bound comes from the plasma decay to neutrino anti-neutrino pair that first was considered by Raphael in 1990. Sorry?
5 minutes left.
Yeah, thank you. Well, and just this process will disturb the cooling of ray chains, and in order not to delay the helium ignition and not to be in a position to the observable data, the bound is on the level of 3 × 10⁻12 Bohr magnetons. So I will skip this. What is very important for astrophysical applications of non-trivial neutrino electromagnetic properties is the effect of appearance of the sterile or nearly sterile right-handed neutrinos in different mechanisms. There is a helicity change in a magnetic moment scattering when left-handed neutrino is transverted to right-handed. There is also the spin and spin flavor precession in the transversal magnetic field. And also there is the same effect, left to right neutrino transition in the matter that have a transversal component, moving matter in transversal component. So, and these effects also applied to the observable fluxes from supernovas. Set a limit on the level of 10⁻12 Bohr magnetons. So about bounds of Milli charge. So there are different processes in astrophysics that are due to possible non-trivial Milli charge of neutrinos, and again we get limits on the in the wide range from 10⁻14 to 10 to minus 17, and the most severe bound is 10 to minus 21, as I have already mentioned, from charge neutrality of the hydrogen atom. So, and the most severe bound from astrophysics was obtained in our paper. We consider neutrino propagation in magnetized and environment, accounting for matter motion or rotation. And we have found that the energy is quantized both to milli-charge neutrino interaction with the background magnetic field and due to weak interaction of neutrinos with the rotating media. There are two types of quantization. We have found an additional quantization due to, and they're very similar to Rayleigh Landau levels for electron in magnetic field. So, and also we just introduce a kind of Lorentz force. So we generalize the electromagnetic part, and we put here the matter-induced charge and quasi-electric field, quasi-magnetic field that is proportional to the rotation frequency of matter, and also on the matter density, and the quasi-electric field is proportional to the gradient of matter density. Well, and implication of all these observations, and in particular accounting for matter for neutrino energy quantization, milli-charge neutrino quantization in the magnetic field, we propose the so-called the neutrino star turning mechanism. So the fact is that milli-charge, electrically milli-charge neutrinos move inside the rotating magnetized star on a curved orbit, and the feedback on effective Lorentz force should affect initial star rotation. And the new astrophysical constraint on neutrino milli-charge come from the demand that we have to avoid the contradiction of the implication of this neutrino star turning mechanism with observational data on pulsars. And from this, we get the most severe astrophysical bound of neutrino milli-charge on a level 10 to minus 19 charge of electron. So just in the last 2 or 3 minutes, I would like to advertise 2 very important new phenomena that are also related to neutrino non-trivial electromagnetic properties. And in particular, it is very well known that there is a mixing and oscillations, the so-called spin and spin flavor oscillations, in the transversal magnetic field due to magnetic moment neutrino interaction with the magnetic field. Well, and in my paper, I have proposed and calculate for the first time the characteristics of the effect of neutrino spin or spin flavor oscillations due to weak interaction of neutrinos with the moving matter. And in this paper, we have found that the possible emergence of neutrino spin oscillations, for example, neutrino left to right, owing to neutrino interaction with matter under the condition that there exists a non-zero transverse current component or matter polarization, is the most important new effect that follows from the investigation of neutrino spin oscillations above. So far, it has been assumed that neutrino spin oscillations may arise only in the case where there exists a non-zero transverse magnetic field in a neutrino rest frame. So I have calculated the probability of neutrino spin transitional oscillations, and the amplitude now depends on the neutrino interaction with the transversal matter current. There is no need for neutrino magnetic moment for neutrino left to right transition. So this effect was, the existence of this effect was confirmed independently by other people, and it is used now for analysis of neutrino fluxes in astrophysics. So, and we also, together with my student, examine all possible transitions that from left to right neutrino, accounting for different combinations of transversal and longitudinal magnetic field, and transversally and longitudinal moving matter, and also discussed the astrophysical applications. So I just skip this, and this is the last point I would like to flash today. There is an inherent relation between neutrino flavor, spin and spin flavor oscillations in a constant magnetic field. It is not possible to consider, as it was before, these two phenomena separately. So we have derived the probability for neutrino spin oscillations from electron neutrino left to neutrino electron right, and have found that there is an interplay between between oscillations on the magnetic frequency and the vacuum frequency. In particular, here is the neutrino probability of neutrino spin oscillations, and it is vividly seen that the amplitude of spin oscillations on a magnetic frequency that depends on the magnetic moment and transversal magnetic field is modulated by the vacuum frequency that is determined by the energy of neutrino and the mass square difference, and vice versa. The amplitude of spin flavor oscillations is in interplay of neutrinos of oscillation on vacuum frequency and magnetic frequencies. So I will just come to a conclusion. This is a brief summary of most important data and facts related to neutrino electromagnetic properties. And I would like to mention that recently, just this year, the new constraints come on the neutrino magnetic moments come from Luke Zeppelin xenon NT experiments, and now the limits are on few 10 to minus 12 Bohr magnetrons. I would like to recall that the expected result from the running new gen experiment will also reach the same value, so something 10 to minus 12. And this is very last my remark. So now we have started a new experiment, as we call it, Sarov-Saturn collaboration, Sarov tritium neutrino experiment, that is now running in due to the program of the National Center for Physics and Mathematics in Sarov. And the goal of this experiment to measure for the first time coherent elastic neutrino atom scattering using the tritium neutrino antineutrino fluxes with the helium detector, and this is the first time it will be measured. And also in this, as we have predicted in our paper published 3 years ago, it will be possible to down the upper bound for effective magnetic moment for neutrino to the level 10 to minus 13. And there was a big conference just 2 weeks ago, the first African conference on high energy physics in Rabat. We have 10 presentations there, and also we announced for the first time this Saturn collaboration, and we hope that we shall succeed in this very ambitious project, and that is based on our paper published in PRD in 2019. And so we would like to invite people to see this project and probably to join our collaboration. Thank you.